So now we are going to talk about Coulomb's law, which is a way to perform calculations that describe mathematically how these charges attract or repel. So this attraction repulsion is going to be based on a force. We call that the electrostatic force. The electrostatic force, because we're talking about electrostatics because the charges themselves are not actually moving. And it's a force, okay? Force is kind of like a push or a pull. So let's just revisit kind of our sweater and balloon scenario for a minute. So I'm going to do this time is remove the wall, and I'm going to add two different balloons. So I'm going to charge up one balloon, I'm going to charge up the other balloon. And so I can see that each balloon is negatively charged. So they're both attracted to the sweater, but I can now see that the balloons themselves are repelled, and that the motion of the balloons is going to be some sort of combination of that attractive and repulsive force. So because there's more than one force acting because of the different objects. So the forces are going to be attractive or repulsive. So if you have two positive charges, the positive charges are going to repel. So like this force right here, using subscripts because we have different objects. So once again, we need subscripts to help describe those. So F12 is going to be the force acting on object 1 being caused by object 2. So this positive charge is creating a repulsive force directly away from the charge. And there's an equal and opposite force, F21, in the opposite direction. Whereas if I have Q1 and Q2 both being of opposite signs, it's an attractive force. So now F12, which is the force caused by charge 2 acting on charge 1, is now pulling charge 1 to the right, and charge 1 is now pulling charge 2 to the left. And I can see that negative charges, like charges, is going to do the exact same thing as the positives, because it doesn't really matter whether they're both positive or both negative. If they're both the same charge, you're going to get that repulsion. And if they are opposite charges, you're going to get attraction. So scientists knew that this was going on long before they could actually calculate and quantify the amount of charge on these objects. So Coulomb's law is a way to mathematically calculate that force. So force is a vector, okay, and it's going to be directed along the line between the objects. They often call that the line of action. So we use R for that, okay? R is like your radius. Sometimes they use a D, the distance between. It doesn't matter whether you use an R or a D. I tend to use the R because that's the way that I learned it. And so that's going to be the distance between the centers of the objects. If you're just looking at individual point charges, that center doesn't really matter. And for the most part, you're not going to need to know the actual size of the objects, because Coulomb's law technically only works for point charges. Things get a little funky when your objects are no longer points in space, like an individual proton or an individual electron. So the direction is going to be either towards or away based on that attraction or repulsion, directly along the line connecting them. And then the magnitude is going to be the force here. And if the subscripts bother, you don't have to use all of the subscripts. You could just use force, F. You don't need the 1 or a 2, because that can be implied. You don't necessarily need the 1 or the 2 here. You can just use R. But we're going to look at arrangements where maybe we have 3 charges, 1, 2, and 3. And in those cases, maybe these subscripts are going to be more important because they're going to tell you which objects are specifically involved. So the subscripts are there to help, but sometimes when you're learning something, the subscripts can kind of get messed up in your head. So then we have this lowercase k, that's called Coulomb's constant. And then you have Q1 and Q2. Now notice here that there are absolute value signs. Those absolute value signs are there just to remind yourself, don't worry about the positives and negatives in your calculation. Just use the magnitudes. So if Q1 is negative and Q2 is positive, don't include the negative. Or if you do, just take the absolute value, because we're going to use diagrams to determine the direction, because that can get kind of confusing. And then if you forget that one's negative and the other one's also negative, and you forget the negatives, things can go weird or wonky. So that's what the absolute value is there for. Sometimes you don't see the absolute value, because technically, if you're writing force as a vector, you're doing K, like Q1 and Q2, over like R, because R is technically a vector, like squared, you might see it written like that. They might not have the arrows on top of Q1 and Q2, because they're implying that you're just going to do the magnitude. Or they might say, oh, we're going to look at the magnitude of the force. So there's a lot of different ways this equation can look. So the important thing is, don't include the positives or negatives when you're doing Q1 and Q2. That's what the absolute value is telling you. So this is an inverse square law. So what this means is that if you were to graph force and distance, you would see that you're going to get an inverse relationship, because your force is proportional to 1 over r squared. So that means your force is going to decrease rapidly with distance. And that's important, because that tells us that these charged particles are really going to be important only at very, very, very short distances. That once you start getting further away, other forces might have a bigger impact. So lowercase k is not technically a fundamental constant. It is always true, though. It's approximately 9 times 10 to the 9 Newton meters squared per Coulomb squared. A lot of times it's written as 8.99, because that's actually more appropriate, 8.99 times 10 to the 9th. You'd have to check the formula sheet as the version that I have on there for you. It's probably the 8.99 times 10 to the 9th, because it's more specific. Some people like the 9E9, 9 times 10 to the 9th, because it's a little easier to remember, but since you don't have to memorize it, just use the version on the formula sheet. And this is also equal to this 1 over 4 pi E naught, where E naught is 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. This E naught is called the electric permittivity of free space. Basically, it's a measure of how well electric fields penetrate a vacuum. So you will see this number again. And so sometimes you'll see problems where they use the 1 over 4 pi E naught instead of K, particularly if it's a problem that doesn't have numeric calculations, where the answers are just symbolic. So, as I mentioned, Coulomb's law is an approximation. It's technically valid for point charges only. It's pretty good for small uniformly charged objects. So if you have like a small sphere, that's going to be okay. We can use it for balloons if we picture that the balloons are perfectly spherical, and it's not that bad. But where it does not work well is when we have objects that are weird shapes, like rods or hoops or different shapes. There are more things that have to go on. You'd actually technically, you can do it, but with calculus, if you need to ever take the calculus-based version of this course, you would learn how to calculate up the forces and the electric fields for each section. Because basically what you have to do is you have to take each individual piece and treat each little piece, each little electron, as a separate bit. And then that little electron is creating a force on, say, that little proton, and then all those forces, you'd have to add up the forces due to each of these little infinitesimally small point charges and then add them up. And that process of adding them up is actually what calculus is. A lot of what calculus is. So we're not going to do that. So we're only going to do situations in which we can reasonably treat our objects as point charges. And then when we look, that R value does technically need to be measured from the center. I doubt they're going to give you a problem where you have to know like the radius of like this object, and then they give you the distances here as R. Like if they did, that would be kind of mean, but if they did, the whole point is that the R that you use in your calculation would have to be directly from the center of one object to the center of the other object in order for that to be true. So there's a cool comparison here. Sorry, I was going to turn all these off. I apologize. And that is between Newton's law of gravitation and Coulomb's law. It's called Coulomb's law of attraction and repulsion. And that is that our gravitational force is equal to G m1 m2 over r squared. And our electric force here is K q1 q2 over r squared. So these are both inverse square relationships. Gravitation involves the attraction of masses, whereas Coulomb's law involves the attraction or repulsion of charges. Oh, please stop. Woo, apologize. There we go. Let's get those in there. Oh, no, scary. Sorry. So both of these are inverse square laws. So the further away you go, the smaller they get quickly. They are a product of masses versus a product of charges. Newton's law is attractive only. Coulomb's can be attractive and repulsive. But what you've done with gravitational force is very similar to what we're going to do here with Coulomb's force. And they're both active all the time because every piece of matter has a mass and has charges. So these are both acting at once. So let's take a look at how these charges and forces come into play. So we're going to look at a hydrogen atom. So a hydrogen atom is the simplest piece of matter that we have. So we have a proton, which has a charge of positive E in the center, and then we've got our electron out here. So our electron has, we're going to use a lowercase m for the mass of the electron, a capital M for the mass of the proton. R is going to be the distance between them. This distance R is actually the average radius of a hydrogen atom. So this isn't just a random value. That's the average radius. So then what you can do is we can use the two equations to calculate these forces and to see which one is more important. Do we always have to include gravitation? Do we always have to include electric force? Have we been lying to you this whole time? You did all of this mechanics and you completely ignored the electrostatic force. Is that reasonable? Do you need to include the gravitational force every time I give you a problem involving charges? Well, let's take a look. So if you were to plug in these values into GMM over R squared, like I said, you can verify this in a calculator. What you end up getting is the gravitational force of the proton pulling on that electron or the electron pulling on that proton is 3.6 times 10 to the negative 47th newtons. That is a very, very, very small value, okay? Even though the atoms are super tiny, because the masses are really, really tiny, the charges are very, very small. Remember, E is 1.6 times 10 to the negative 19th coulombs. These are very, 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 very tiny values. Now, when we calculate the electric force, so once again here they're using 1 over 4 pi E naught instead of K, but you could use the K instead. K is our 8.99 times 10 to the 9th, or 99. You get capital Q, lowercase q. Okay, this is basically just going to be positive E and another E, right? Because we don't include, we take the absolute value, okay, of those charges. So that's basically E squared. This is, I can simplify this down to K E squared over R squared, okay? We end up getting 3.6 times 10 to the negative 8th newtons. Now, this is really, really impressive because this is times 10 to the negative 47th. This is times 10 to the negative 8. Same distance, right? This is the electrostatic force of attraction between the proton and the electron. So what ends up happening is with these values, this tells us that this is basically negligible. So when we're looking at individual charged particles, we can ignore the masses. Now, there'll be examples like the one that we look at next, kind of saw a little sneak peek of that, where we have non-negligible masses, and where actually the charges and the masses both come into play. But if you are looking at a situation where you're looking at just protons or just electrons or charged objects in space, they are probably not going to give you masses. And even if they do give you masses, really what matters is the electric force. So if I give you like an arrangement of charges, kind of like I talked about before, and I want you to find the net force on, say, charge 1 due to the other charges, the net force only needs to include the electrostatic charges using Coulomb's law. You do not also have to include those masses, the gravitational forces, because those gravitational forces are going to be so small. Now, here's an example where we actually have to consider both. This is going to look very similar to a problem that you had coming out of dynamics, where maybe you had objects hanging on ramps with your mechanics course. So here we have two identical balls or spheres of some kind have mass m and charge q. They hang from similar strings of length L, and after equilibrium is reached, so we hang them, they're gonna repel each other apart because they're identical, so like charges are gonna repel. They're gonna reach equilibrium so that they're hanging at this angle theta. And what we do is we want to find the charge q as a function of theta and L. So this might be something different that you might have seen. Everybody's Physics 1401 was a little different. But solving problems in variable format and not including numbers is actually really handy when we're doing things with like Coulomb's law and stuff. Because of that scientific notation, the chance of you making a calculation error are pretty high, especially under the stress of a test. So a lot of times I'll have you solve problems just in variable format and not give you any numbers. Please don't freak out when you see them. Just go through the steps that you would normally go through. Just instead of plugging in numbers at the end, when you have your equation, you're done. So I'm going to be modeling how I expect you to solve problems. You will not have to do a ton of problems where you have to show your work, except for on labs, as your tests are going to be a combination of multiple choice and conceptual short answer. But if you follow these steps every time you solve a problem, you're more likely to get to that correct answer when you get to the point where you have to plug in numbers. So please use this as a model for how you should be solving all of your problems. So what I want to do is, I know that this is an equilibrium, so I need to consider forces. So anytime I solved a problem in mechanics involving forces, I always drew a free body diagram. So I'm going to focus on this ball right here. So there is going to be a gravitational force pulling down, and there's going to be a tension going along the string. So that's going to be my tension force. And then, because these are like charges, there's going to be an electrostatic repulsion. So that's going to point away from the other charge. Now we have to be careful, because that repulsion is going to be based on this separation distance r right there between the center of those two spheres. And that is not actually provided for us in our problem. So since my forces must be in equilibrium, I need to break this into x and y components. So what we're going to have here is we're going to have x and y components coming through. And I'm going to break this tension into a triangle and make those x and y components. So my angle theta is up here at the top. That is going to be the same as this angle right here. You can use your opposite sides geometry to figure that out. So I'm going to draw here my FTY on this side and my FTX coming across over there. And in order for this to be in equilibrium, I can see that in the x direction, my net force in the x direction, in the positive x direction, is going to be FTX. And in the negative x direction, it's going to be my electric force. And that has to add up to 0. In the y direction, my net force in the y direction is going to be FTY going up minus FG coming down, and that has to equal 0. So depending on your teacher, you might have used different symbols for the forces and so forth. It does not matter as long as you're using an acceptable version that communicates your forces well. This is just the way that if I was teaching 1401, this is how I would have set up my forces. So then this tells me that my tension force in the x direction has to equal my electric force. Now, I don't know that tension, and I'm looking for charge as a function of only theta and L. I'm also allowed universal constants. For example, I can have K in my answer. I can have lowercase g for the acceleration due to gravity in my answer. So I'm going to need to find a way to eliminate tension. So I have tension in two locations. I have Fty is also equal to Fg over here. So since tension can't be in my answer, and I don't have numbers, so I can't calculate it, I could find an expression for it. What I'm going to do is I'm going to use my trig. So Ft is over here, that's my hypotenuse. Fty is the adjacent side, and Ftx is the opposite side of that triangle. So that means Ftx, which is the opposite side, is going to be Ft sine theta. And that is going to equal my electric force, which is going to be my K, Q times Q over R squared. So they both have the same Q, so I'm just going to use Q times Q. I don't need to use Q1 and Q2. Now over here in the y direction, my Fty is going to be Ft cosine theta because it's the adjacent side, and that's going to equal m times g. Well, I think the one over there on the right is a little bit easier, so I'm going to divide both sides by cosine theta and get that Ft is equal to mg divided by cosine theta. And then what I can do, since that's not allowed to be in my answer, I can take this and I can sub it in over here. So I get that Ft, which is mg over cosine theta, times sine theta is equal to kq squared over r squared. Q times q is q squared. So this is looking better. The order over here doesn't matter because I can picture that my sine theta is over 1 and I could rearrange, and sine divided by cosine is just tangent. So I can rewrite the left side as mg tan theta is equal to kq squared over r squared. Now this is looking pretty good. I'm looking for Q, and I can see that I can rearrange and get Q by itself. One problem I notice is that I'm allowed L in my answer, but I'm not allowed R in my answer. So I need to find a way to get rid of R. So if I look at my triangle here, so there's this big triangle here. L is the hypotenuse of that triangle. And I've got my angle theta right here. R divided by 2 is the opposite side. So that tells me that R over 2 is going to be my opposite side, is going to be L times sine theta, because opposite's based on sine theta. So this tells me that R is going to be 2 times L sine theta. So I could take that and sub it in for R over here. So I get mg tan theta is equal to kq squared over 2L sine theta squared. And then I'm going to multiply that to the other side to get it out of the denominator. So I get mg tan theta times 2L sine theta squared is equal to kq squared. I can then divide both sides by k. So when I do that, the k goes away over here. And then I can take the square root on both sides to cancel out the square. So I get that q is equal to the mg tan theta over k has to stay there, and then the 2L sine theta, because that's inside the square and multiplication doesn't matter, I can actually pull that in front, 2L sine theta, and then all that is times the square root of mg tan theta over k. And that would be the value of the charge. Oops. And you could plug in numbers at this point and figure out what that value was. But some things that it tells me that the longer my rope is, the bigger the charge would have to have been to create that angle. It tells me that if my gravitational force was larger, then I would have had to have a larger charge. So there's a couple different things that I can learn with this equation in variable format that I couldn't if I just plugged in numbers. So that would be our answer. So the next one we're going to look at is a standard problem where we have charges arranged in an orientation. So this is not going to be one where we have to involve gravity. So we have a positive charge Q1, which is equal to positive Q, is located at distance D along the y-axis from the origin. A second positive charge Q2 is equal to positive Q, so these are identical charges, is located at the origin. And then a third negative charge, in this case, Q3, which has a charge of negative 2Q, is located on the x-axis, a distance 2D away from Q1. So the first thing you would want to do is you want to kind of draw this out. If there's not a picture for you, you want to draw this out. Don't try and do any calculations in 2D without having this laid out. So our goal is to calculate the net electrostatic force. So that's basically our net electric force on Q1 due to the other two charges. So if we were to lay this out, so we have on our y-axis, we have Q1 is located away, and then Q2 is located at the origin, so I could draw on my y-axis right there. And if I draw on my x-axis, Q3 is at a distance of 2D away from Q1. So you have to be careful. It's 2D away from Q1. It's not a distance of 2D away on the actual x-axis. So you have to be kind of careful with the wording. So our goal is to calculate the net electrostatic force on Q1, which is this one right here, due to the other two charges. So the first thing I have to do is I have to draw out my forces. So I'm going to assume that Q2 here at the bottom, those are both positive charges. So it's going to be creating a repulsive force. So it's going to be pointing upwards and pushing Q1 away from that. So I'm going to call that F2 because it's the force being caused by charge 2 on charge 1. And then when I look at Q3, Q3 is negative, so it's actually attracting Q1. So it's going to be pulling Q1 towards it. It has a bigger charge, but it has a larger distance. So those are going to kind of work against each other. So I'm just going to draw that at some length here. I don't know the exact length. I'm going to call that F3. So those are the two forces that are acting. So once again, I'm going to have to break this into X and Y components. So I'm going to draw in here kind of X and Y. And my F3 is at an angle. So I'm going to, let's see, it doesn't really matter. What I'm going to do is I'm going to use this triangle right here, so then I'm using this angle theta. So that's going to be F3x, and then coming down is going to be F3y. I'm using this angle theta because it's matching this bigger triangle, so I can use some kind of similar triangles if you wanted to, or just keep our sines and cosines kind of along with that. So if I was to write out the net force in the x direction, that's just going to equal F3x. So that one's a little bit easier because it's only one force is in the x direction. And then our net force, oops, sorry. Okay. Our net force in the y direction is going to be upward is going to be F2, downward is going to be F3y. Now, we don't really care. These are not in equilibrium, doesn't say that. So we don't know if this is going to equal MA or 0. It doesn't matter. We're just looking for that net force. Probably non-zero, if we had to guess, in the y direction. Because there's only one particular setup that would give us those forces being exactly equal. So when I look at F3x, F3x is the opposite side of that triangle. So my net force in the x direction is going to be F3 sine of my angle theta. And then my Fy net force in the y direction is going to be F2, and then F3y is going to be based on the cosine of that angle. So if I wanted to go through, I could take a look at my triangle. So for the sine theta right there, my theta, I can actually find theta using my bigger triangle. So I have my bigger triangle right here. So that angle theta, I have an adjacent side that is equal to d and a hypotenuse that is equal to 2d. So if I use cosine of my angle theta is going to equal d over 2d. So that's just going to equal 1/2, because the d on top and the d on the bottom are going to cancel. So cosine theta is going to be 1/2. For my opposite side, I could use the Pythagorean theorem to find the third side right here if we wanted to do that. So our 2d is our hypotenuse squared, has to equal d squared plus, I'm going to call this x right there, plus x squared. So if I subtract the d squared to the other side, I get that x squared is equal to 2 squared, which is going to be 4 times d squared minus d squared, so that's going to be 3d squared. So x squared equals 3d squared. So you take the square root on both sides. So x is going to equal to the square root of 3 times d. So now that we know that, we could find sine theta. So sine theta is going to be our opposite, which is the square root of 3 times d over our hypotenuse, which is 2d. So sine theta is going to be the square root of 3 over 2. And if you've got your unit circle memorized, you might have been able to figure out already that if you already knew that cosine theta was 1/2, then you had to have the square root of 3 over 2, because this is going to be a 60-degree angle. So you might have already had that memorized. That's awesome and fine. But if not, this is how you could figure that out. Also, if this was a problem with numbers, you could just plug in numbers and get those answers right away. Like I said, I'm doing these ones without numbers because it gives you practice for the ones that don't have numbers. And I'm assuming that if you can do the ones that don't have numbers, adding numbers in is not as much of a problem. So coming up here to my force calculations in the x direction, my net force in the x direction is going to be F3. So this is going to be Coulomb's law, so that's going to be K. And F3 is between my negative 2Q charge and my positive Q charge. So that's going to be Q times 2Q. Remember, I don't need to include the negative. And then that will be over the distance between them squared. So that's going to be R squared. So that's going to be 2D squared. And then times sine theta, which is the square root of 3 over 2. So I can simplify this down a little bit. So the 2 and the 2 cancel right here. I can combine the q squared. So my net force in the x direction is going to be the square root of 3 over 4, because 2 squared in the denominator is 4. And then I'm going to have kq squared on top and d squared on the bottom. So that's my net force in the x direction. And then in the y direction, I'm going to have to do something similar. So F2 is between positive q and q. So that's just going to be k, q times q, which is q squared, divided by the distance d squared, minus F3, which is going to be the same a little bit over here. So that's going to be k q times 2q over my 2d squared. This time, cosine theta is 1/2. So we still have that the 2 and the 2 cancel over here. So we get that our net force in the y direction is kq squared over d squared minus kq squared over 4d squared. So combining like terms, I would need to add a 4 over 4 over here. So my net force in the y direction is going to be 3kq squared over 4d squared. So they look really similar, but they're not the same. So that gives me my net force in the x direction and my net force in the y direction. If I wanted to find my actual net force, I then have to use the Pythagorean theorem to find the combined magnitude. So my net force magnitude is going to be equal to the square root of my net force in the x direction squared plus my net force in the y direction squared. And I wouldn't even bother like calculating this out or plugging it in or anything. I would just leave it as square root of 3 over 4 kq squared over d squared squared plus 3kq squared over 4d squared squared. Okay, and that is what our net force is. Okay, that's the magnitude of that. If we wanted to find the direction that net force is at, then we could also find that our theta is tan to the minus 1 of our opposite, which would be our net force in the y direction over our net force in the x direction. Okay, so you could do that to find the angle if we wanted. Most of the time they're going to ask you for the magnitude of the net force, which would be found there. And once again, if you have numbers at this point, you could just plug in numbers, and the numbers aren't that bad. All right. So I hope that gives you some examples for how to solve problems involving Coulomb's law. If you need more help, there's lots of tutorial videos. Go to the additional tutorials link in D2L. There are videos from Khan Academy, Flipping Physics, and Organic Chemistry Tutor that will show you how to use Coulomb's law. They probably don't do everything non-numerically like I did here in variable format. They usually just have numbers in them. They plug them in for you as you go through. So you have that as an option. I like kind of stepping it up a little bit here so you can see what the hardest of the types of problems might look like here in our video lectures, and leave the rest for you to find as you need.